Great. Well, I'll start ahead. Thank you, everyone. We're about 6 minutes past the hour. Thank you for coming. I'd like to welcome you to the GISS Lunch Seminar. I'm really happy today to say that we have Emma Knowland from the Global Modeling and Assimilation Office presenting. And I've known Emma for several years right now. And Emma's, again, she's in the GMAO and she's been there for a few years. She received her Bachelor of Science from McGill University and then her PhD from the University of Edinburgh. And at Edinburgh, she was working with Ruth Doherty and with Kevin Hodges, doing, among other things, an analysis using storm track algorithms to investigate the behavior of long-range transport and air pollution, specifically within storms over the North Pacific and North Atlantic. So Emma's has been really intensely involved over the past few years in some exciting new efforts within the Global Modeling Assimilation Office to produce composition forecasts. And so she'll describe some of the work that she's been doing with colleagues there. And I just, before transitioning to Emma right now, I just want to indicate that what we'll be doing is, as we've done in previous seminars, if you have a question, so everyone by default has been muted, but if you have a question, please indicate that in the chat. So you can either write the question or more simply, you can say, I have a question, and then I will unmute you, and then you can ask the question. And so this should go probably to about 2 p.m., but we also have half an hour after in case things move. So this is being recorded. And with that, Emma, whenever you're ready, I'm going to turn off my video and audio, but please feel free to start.
Great. Thank you so much, Claire, for the introduction and the invitation to talk today at GISS. Hopefully another time I can actually come up to New York and visit and meet everybody in person. And as Claire said, yes, please do interrupt. It's been a long time since I've had to talk for 45 minutes straight. And though I'm very much known as a talker, you might find that I have to take a breath and a drink of water at some point. So please don't be shy. The work today that I'm presenting on is air pollution forecasting from NASA's Global Modeling and Assimilation Office, or GMAO. This work is done in collaboration with several members from GMAO, as well as from the Atmospheric Chemistry and Dynamics Lab at Goddard. And I've highlighted a few of the names here, but there's many more behind the scenes that get our model running and working beautifully, including in the production system. And so our office, the GMAO, it develops and maintains a suite of Earth system models that are known as GEOS. And this is mainly designed to advance the use of satellite data products. And so hopefully what I can show you here is this fancy animation. And so satellites provide information on fire location and emissions, which are indicated here in this animation as the red dots, like you can see over South America. And the aerosols are particles in the atmosphere. They're emitted and produced by both anthropogenic and natural sources before they're transported. And so you can see dust in the orange being transported across the Atlantic. You can see the sea salt in blue being wrapped up in the weather systems over the North Atlantic. We've got organic and black carbon in green, as shown in the biomass burning regions like in Africa. And then we also have sulfates in the model, and those are those white colors, as you can see now over Asia. So our flagship GEOS numerical weather prediction model, it already simulates weather as well as aerosols, as demonstrated here in this animation of the GEOS nature run. And so for the numerical weather prediction, we have two main branches of forecasting and reanalysis. The GEOS Forward Processing System, or Gsfp, that's our state-of-the-science NWP model, which it's roughly updated every 6 to 12 months with either some type of new observing system, or we've made some updates to the model physics. And then a reanalysis is when we take that latest model of the Gsfp, we freeze that model, and we reanalyze past observations in order to have a consistent data product without the model underlying changing. So it's been about 5 years, I think, maybe a little bit more now, since we released Mirror 2. and many advancements have been made to GeoSFP. And so it's quite exciting right now around the GMAO as we're working on our next reanalysis product. One lesser known near real-time product is the GeosFP for instrument teams. And that uses a GEOS model that's very similar to MERA 2, but it has some changes to the observing system so that we don't ingest information from satellites in the data assimilation system whose retrieval teams need some type of prior information from the model. And so since this model is static, it's really ideal for us to use as a driving meteorology for what we're calling our composition forecast system, or GEOS-CF. And so here what we've done is we've taken the GEOS NWP model and we've expanded on it by coupling it to the GEOS-Chem chemistry model in order to have a composition forecast. And so now the GeoCf, it's one of GMAO's official near real-time products with a focus on providing information to the community on air quality. We started this project back in early 2017 with our first experimental GeoS-CF system. And then we had a soft release in late 2018 with our imagery only of our forecasts on our website. And then in September 2019, we were finally able to release the data to the public. And so GEOS-Chem, it's a state-of-the-science chemistry transport model. It's maintained by folks at Harvard, but it also has a global community of developers and users. So this means that we're not doing the development in-house at NASA Goddard. It's a complex chemistry model. It's got full tropospheric and stratospheric chemistry with about 250 reactive species and over 700 chemical reactions, and the version 12 that we have been currently running with. I've just shown here two snapshots from some animations that were made by the Goddard Scientific Visualization Studio, or SVS. Highly encourage you to check them out if you haven't already seen what SVS makes. They're beautiful. And these were released in 2019 when we released the GEOS-CF to the public. And so what you can see in the top right is highlighting an animation of surface ozone. And if you look at this animation, you would see the diurnal cycle of ozone with the highest concentrations are shown in white. And these are generally during the day close to urban centers. So you can kind of see here, even without the country borders, which are hard to see, you can see North America as well as like across Asia into Europe. But at nighttime, the ozone gets very low due to NOx titration. And so you can actually see parts of China almost blacked out. The animation on the bottom left here highlights the complexity of the GEOS-Chem chemistry, showing 96, so not even half of the chemical species that play a part either directly or indirectly in simulating surface ozone. And so this is just showing a few of those species, and you can see the interaction with the large-scale weather systems, and in some places, maybe some of the emission sources, including we use a climatology of ship tracks. And so you may be more familiar with the go-kart mechanism, which is used in GeoSFP and MERA 2 to simulate aerosols, like the one I showed in the opening animation. And GEOS-Chem, it has its own aerosol scheme. So we get both the reactive gases like ozone, NO2, CO, but we also get the aerosols. And because of the coupled chemistry, GeoS-Chem is actually able to simulate things like the secondary organic aerosols, which go-kart does not. And so each day, starting around either 2 or 3 o'clock in the afternoon, depending on daylight savings, we launch the GEOS-CF system, following the completion of the GEOS FPIT 12Z run. And this is because in order to have the best initial conditions for our 5-day forecast, we first run what we call a meteorological replay. And so this is where we take the GEOS model, and instead of running with a full data assimilation cycle, we use the information from a previously run data assimilation system. And this saves both on time as well as on compute resources and just model complexity. And so now how this works is if you had a GEOS model and you've replayed with the exact same model, you should have the exact same results. And this way, if we use a model that's similar, we can save time whenever we want to rerun a previous time period constrained by observations. And so Clara wrote a fantastic paper about replay technique a couple years ago. So if you have any questions on this that I can't answer, Clara definitely, hopefully can. So now, if we were running this as a data assimilation system, our replay would be considered our analysis. But since there's no direct data assimilation in this system, you'll hear me continuously use the word replay to refer to this time period. So what we do is we rerun the past 24 hours now with the chemistry. And this is computationally still very expensive. And so this is run separately to the GeoSFP system in near real time. It uses the compute power of 3,500 CPUs, and it still takes 8 to 9 hours to do this one-day replay and 5-day forecast. And we run this at a very high global resolution of 1/4 degree, and on the full atmospheric levels for GEOS, so that's from the surface all the way up into the mesosphere. And this way we get the chemistry and the meteorology on the same temporal and spatial scales. And so what you can see here in this animation is the hourly average ozone from at the surface. And what you can see is that we're actually able to capture extreme events, the diurnal cycle in ozone, as I kind of mentioned earlier. You can see this pollution outflow coming off of Asia, and other kind of frontal features here, like over the North Atlantic and coming off the coast of the US. And so running at 1/4 degree or 25 by 25 kilometers, it's 10 times higher resolution than most of the chemistry models that are done with GEOS-Chem. And so, as I alluded to, we try and release to the public high temporal frequency data with a focus on air quality. So we have meteorological fields and pollutant concentrations on what we call the surface, which is the model's lowest layer, which is roughly about 130 meters thick. And we save these diagnostics at 15-minute intervals, and which make for great animations. But generally, the 1 hour average is used when we're comparing against surface observations. But we also release 3D files of both composition and meteorology together. And since the end of each day's replay segment is the start of the next day's replay segment, we're able to stitch the replay files together and have a continuous time period since January 1st of 2018. And so generally, our forecasts remain available to the public for a 2-week period. However, we do have forecasts of the surface concentrations of the 5 most requested pollutants available to the public since January 2019 for research. And so that would be ozone, CO, NO2, PM2.5, and SO2.
Emma?
Yeah.
Hi. So I have a basic question actually about the 5 days. Was that 5 some kind of optimization based on some skill analysis, or? Yep.
That's a great question. No, so when we were first setting this up as the experimental system, it would start at just about midnight, so instead of in the afternoon. And it would finish its 8 to 9 hour replay plus forecast by basically the time that we got to work. So it was kind of one of those things, like 5 seems like a time period that we usually look for forecasts. So I don't think we ever really rocked the boat from beyond that 5. I don't know if we would in the future, try and do some other type of length. Or different times of the day, like maybe since we only do it once a day, like other operational centers, which we are not an operational center, they tend to do maybe a 0Z or a 6Z forecast as well. So depending on where you're located, there might be like a different time to actually launch your forecast so that it has maybe a more value or a different added value to the community.
Yep, makes sense.
Yeah, so anywhere from like 2 days to 10 days would probably, you could easily find end users for like a composition forecast.
Great, thanks.
Yeah. Yeah, so there are a few ways in which you can access the GeoS-CF. First, we have the GMAO's mobile-friendly website. So encourage you, if you are interested, to play around and see what we have, would be to click this link up here. And from there, you can access the different ways to actually download the data. So we have the NASA data portal, so you can directly download these NetCDF files of the GeoS-CF. Or since these files are quite large, you can remotely access them through OpenDAP using any number of programming languages, Python, IDL, R, etc. Should be able to access that data just by using the URL. I do encourage you, if you've seen the CF website from Fluid before, to occasionally return back to it, because we work directly with the Fluid developers to bring new capabilities to the GEOS-CF, and so we definitely have things set up ready, hopefully to come soon, which is quite exciting. But you don't need to worry about writing these down necessarily. The main link here at the bottom of each slide will bring you to any one of these different websites. So like I mentioned earlier, right now there's no direct data assimilation of chemical species in the GeoS-CF system, yet there is near real-time information that's constraining parts of the system. So we use the satellite-based emissions from the near real-time QFED, that's the Quick Fire Emission Database, to inform the system of biomass burning emissions. And so here in the center, you can see a MODIS image from November of 2017 during the peak fire season here in India. And you can see these red dots, those are the fire locations, and you can kind of see the smoke from the MODIS map behind. And then on the left is a time series of PM 2.5 for Delhi from that same period. The black is observations, and the daily GeoS-CF, the replay is in red. And then as we go out to the 5-day forecast, it transitions to more yellow colors. And so in the forecast, we persist the biomass burning emissions. So there can be large discrepancies between the forecasted PM 2.5 and the actual observations, depending on meteorological conditions and fire intensity. Ooh, gotta take a breath. Sorry if I'm speaking too fast, let me know. In order to take advantage of the established GEOS Ozone data assimilation system, before we could implement such a system in the GeoS-CF, we developed this way of actually nudging the stratospheric ozone only towards the Gsfp assimilated ozone product, which includes OMI, total column ozone, MLS, stratospheric profiles of ozone, and then since March of 2019, also OMS, ozone. And so what you can see here is that we have a good agreement between the GeoS-CF in pink and the OMI total column ozone in gray. And so furthermore, what goes into the model helps us to correctly simulate air quality. So we use monthly averages from the HTAP version 2.2 for anthropogenic emissions. And then we've got several online parameterizations for things like dust, sea salt, and lightning, as well as our biogenic emissions. And then, like I said earlier, we use the near real-time QFED. And here we actually have 35% of the fire emissions are emitted above the boundary layer, and that's evenly between 3.5 and 5.5 kilometers altitude following the Fisher et al. 2014 paper. You might also be interested in, we have the surface mixing ratio boundary conditions for the ozone depleting substances following the WMO's 2018 assessment emission scenarios. And then furthermore, to improve on these base emissions, we use a bunch of different scale factors, such as annual gridded scale factors based on satellite data to better capture sources and trends. Specifically, we use FAILU's OMI HTAP emission inventory. But I also want to mention that because we live in this COVID-19 era, any changes in the anthropogenic emissions due to COVID-19 restrictions are likely not picked up in the model. And I'll talk a bit more about that in a little bit. And then in addition to these monthly average anthropogenic emissions, we further break these down into hourly values that are sector specific, day of week, as well as diurnal scale factors. And so this can be seen quite nicely in this image on the left here of NO2 over Europe, highlighting here Zurich, Switzerland, which is where Christoph Keller is from. So that's one of the reasons it's highlighted here. And so on the bottom, again, we have the observations now of NO2 in black and the model replay in red to the forecast in yellow. And you can actually see here on the weekends versus the weekday, though the model does a decent job of capturing the diurnal variability, you can also see that weekday to weekend here with the lows on the Sunday, the 22nd and the 29th quite nicely. So now that I've given an introduction to the CF, I'm just going to show a few slides on the evaluation efforts that we've been doing over the past year, and then also show you some examples of how the GeoCf has been used. And so the following slides, they cover the results from work done over the past year to evaluate the GeoS-CF 2018 to 2019, mostly the replay, but also the forecast from the 2019 period. And this work was done by a group of scientists at Goddard from the Atmospheric Chemistry and Dynamics Lab, or Code 614, as well as the GMAO. And outside of this group and the reviewers of Christoph's paper, this is very new material. It hasn't been seen by anybody else. So I'll start first by showing the observations that we used in the evaluation. The blue circles are observations available in the OpenAQ database. OpenAQ is a nonprofit which compiles publicly available air quality data in near real time into an open source database. And we've used this right from the beginning in 2017 with the development and evaluation of the CF. There are still many gaps, as you can see. And some of that is because OpenAQ, the programming has to be written in order to pull in data. So you can see that New Zealand doesn't have any OpenAQ, but there's definitely observations in New Zealand. But a lot of it also comes down to that these are in areas that are either countries that can afford these very expensive monitoring equipment on the order of hundreds of thousands of dollars. And so because of that, a lot of places are still unmonitored. In yellow are the AeroNet for aerosol optical depth, and then for CO, ozone, and NO2, for more background observations, we've relied on the Global Atmospheric Watch, or GAW, World Data Center for Greenhouse Gases and Reactive Gases. And then we have ozone sondes as well from the World Ozone and Ultraviolet Radiation Data Center. And then some of these we've actually grouped into regions, these 6 regions, and we'll show that more in a moment. And so first we'll look at model skill, and OpenAQ sites here are shown in the circles in all plots except for the CO, and then the background sites are indicated by the diamonds, except here in CO with the gauze actually still a circle. For ozone, you can see that the model does really well in capturing background ozone throughout the year. The skill score is very good at these locations. And it's not surprising that the skill scores worsen for OpenAQ because it's hard to compare that background average for your 25 by 25 kilometer grid box to these point source measurements. And we see a similar story for NO2, but for the GOS sites, there's only a small sample size of 6 stations, and so that might be one of the reasons why we see this large variability month to month in things like the normalized mean bias. The GeoCF, it generally overestimates aerosol concentrations, though the model scores are better for AOD comparable to the other species at the background sites. And this is because there's actually excessive sulfate aerosols owing to the use of the outdated anthropogenic SO2 emission database, HTAP having a base year of 2010. And so you can also see that high bias in the SO2. Another reason might be that for PM 2.5, we're assuming 35% relative humidity, while observations in OpenAQ may assume the dry particulate matter. And so looking first at the GAW network, the background in purple is the average surface concentrations from the GeoS-CF. And then overlaid on top are the monthly time series of surface ozone from GeoS-CF in those purple time series. And then the GOS sites are aggregated by region and colored accordingly. And so in general, the seasonal cycle varies by region, and the GeoS-CF is able to capture much of that variability. In particular, in North America, we'll highlight that springtime peak due to stratospheric intrusions. And then like in Europe, you can see that summertime maximum due to pollution. Though we do see the model tends to overestimate summertime pollution in Asia, likely not able to capture as much of the NOx titration that's actually occurring. And then ozone underestimates in the southern hemisphere. That's been linked to an overestimation in ozone deposition, and this will hopefully be improved in a later version of GeoS-CF that we're working towards with a newer version of GEOS-Chem. So now looking at surface ozone aggregated here by region, but looking at the OpenAQ sites, that would be the black line are the observations, and then GeoS-CF is in pink. The model generally overestimates surface ozone in Europe and North America, as well as South America and Australia, by about 5 to 10 parts per billion, in particular in those summer months here in North and South America. Whereas in contrast, the model tends to underestimate ozone in Asia and Africa by as much as 20 parts per billion, as you can see here. These differences are larger than what was seen at the remote GOS sites, suggesting that it really comes down to that subgrid scale factors and that nighttime loss of ozone by NOx titration. So to look at that in more detail, we looked at just the afternoon ozone from noon to 4 p.m. local time, and that actually helped to reduce the bias by up to 5 ppb. And that's really noticeable in Asia and then South America and Australia. Taking a quick break from the surface observations, we look at GeoS-CF and tropospheric ozone columns. And that would be the map here on the back, the 2018 tropospheric ozone columns. And then we have the same field, but from the 28 ozone zones. And you can see that GeoS-CF generally captures the spatial distribution of the observed tropospheric ozone, but it does tend to underestimate over polluted regions, such as over these European sites, as well as sites near Japan. And then on the right shows profile comparisons from 3 selected sites. Those are circled in blue. And the model output is sampled at the nearest grid point and launch time for each sonde. The thin dashed lines are daily profiles in 2018, and then the thick lines are the annual mean. And so GeoS-CF in general captures the observed profile shape over these 3 stations, and in the paper, we actually show these comparisons for 24 stations for 2018 to 2019. And what we can see in the paper as well is there tends to be this low bias in the free troposphere, as seen in these 2 examples here in the bottom row. And then, as I said earlier, there's only a few GOS sites that actually measure NO2, and these are located in Europe, and we focus on the non-mountain sites to avoid any misrepresentation of the grid box when there's difficult orography. And so as shown on the left, you can see there's generally good agreement at these 6 sites to the model. And then on the right-hand side, looking at OpenAQ, which were more the urban sites, we can see there's excellent agreement in North America, in Africa, as well as Asia in the summer months. But there tends to be a low bias in Europe and South America. And so this may be related to some of the NO2 instruments overestimating NO2 and actually reporting something that's a bit more like an NOY. Model bias for aerosol optical depth, as shown on the left-hand side, it's highest in Europe and North America. And in these plots, we've actually included a dashed orange line, and that would be the aerosol optical depth, but without the sulfate aerosols, since there's an overprediction due to the excessive SO2 emissions in GeoSCF. And so these sulfate aerosols make up to 50% of the total AOD over Europe, North America, and Asia, and generally leads to a better agreement, except maybe here in Asia where we actually see now maybe a low bias. And then similar to the AOD comparisons when looking at PM2.5 from the OpenAQ database, we tend to see the model overpredicts PM2.5 in Europe, North America, Asia, and South America. So in addition to the excessive SO2 emissions, there might also be an overestimation of biomass burning emissions in GeoSCF because the enhancement factors in QFED, they are designed to match MODIS observed AOD within the go-kart model, and that may lead to some of the bias in GeoSCF aerosol concentrations, especially in regions with fire seasons like Africa and South America. And then another look at vertical profiles, and this time the hydroxyl radical OH. This one comes from Julie Nicely. She used ATOM 4 measurements from the Penn State ATHOS instrument, and then mixing ratios from hourly output from GeoSCF, which she interpolated to the flight observations. And then she aggregated these into 100 hectopascal pressure bins, as you can see in the left-hand side. Number of observations ranges from about 600 to 3,500 here at the top. And these box and whisker plots show the median in the line and the mean as the diamonds. And so as you can see, OH from GeoSCF matches the observations remarkably well, right up to about 300 hectopascals, with a modest disagreement at the 200 hectopascal level, which may be due to measurements being conducted within the stratosphere. And so despite the model doing well to predict the tropopause height, it still overestimates the OH abundance present at these altitudes. So we need to look a little bit more probably into the UTLS chemistry. This slide highlights the significant improvement to CO in GeoSCF compared to previous studies, especially over the Northern Hemisphere. The left figure is reproduced from a 2013 paper that shows the CO difference between ACMIP model, multi-model mean, and MOPIT CO at 500 hectopascals for the period from 2000 to 2006. And then the right panel shows the CO difference between CF and MOPIT at 500 using the same color bar. And so GeoSCF significantly improves the CO simulation, except maybe over South Central China, where there's still a persistent positive bias. But the negative bias in the Northern Hemisphere mid-latitudes is otherwise generally lower by about 15 ppb. And as I show in these like purple or pink circles, I'm trying to draw your attention to where we've seen an improvement over Northern India, tropical Eastern Pacific, South America, Central Africa, and Indonesia.
Sorry, Emma, just really quickly. Do you think that's just reflective of the improved OH, or is there maybe something else going on?
Can you repeat your question, Clara?
Sorry. Do you think that's consistent with the good OH that you were showing in the previous slide?
Yes, I think so. And hopefully it continues. Yeah, but I think it definitely has helped.
Yeah, thanks.
My understanding, it was definitely even an issue earlier in GEOS-Chem version, so we're quite excited to have seen this improvement. So up until now, I've mostly focused on the replay evaluation. And so we did look at forecast skill for the composition forecast system. The -1 on these figures is what I'd shown earlier for the replay. And now with the forecasts, we have the normalized mean bias, root mean square error, and the correlation for ozone, NO2, and PM2.5. And since the model doesn't directly assimilate trace gas observations or make any type of adjustment in near real time for emissions, the difference between the replay and the forecast is mainly the changes in meteorology, which not only impacts the transport of the species, but also deposition and any of the online emission parameterizations. Such as the near real-time QFED, it's updated once a day. And so actually half of each replay and the 5-day forecast have persisted biomass burning emissions, which can really impact concentrations both close to and downwind from the fires. And so one approach to deal with these issues related to model biases from things like the subgrid scale errors or uncertainty related to the meteorology and the treatment of things like emissions, deposition, and chemistry, one can create and train a machine learning algorithm to bias correct the forecasts at the individual observation sites in a post-processing step. And so Christoph Keller did just that. And I'm showing here an example for Leon, Mexico, which is located about 250 miles northwest of Mexico City, up in the mountains. And so what you can see here is there are 2 observation sites that are located within the same GeoS-CF grid box. And on the right-hand side, the pink is the model, and you'll see that those are the same for both locations, but the black observations are slightly different. And so the bias correction methodology, it's described in Christoph's recent ACP paper, if you want more details. It uses XGBoost algorithm to correct the hourly average model predictions of ozone, NO2, and PM2.5 using local meteorology and atmospheric composition, as well as what's predicted from the GeoS-CF. It uses meteorology, chemistry, and calendar information. We don't forecast emissions, so that's not used in this version. And since the model biases are often site-specific, a machine learning algorithm is trained for each individual site. And so I'm sorry this is green, it's still ozone and not NO2. But what you can see here is that the model plus the machine learning using that bias correction factor now has a much better agreement with the observations in black. And so Christoph used this type of algorithm and trained on each individual site for all those observation sites. And so what you can see here, the diamonds were the mean from the original GeoS-CF data, and using that machine learning algorithm, the forecast skill for the individual sites for the forecast has greatly improved. And we actually have 2 partner cities already, Rio de Janeiro in Brazil and Quito in Ecuador, who actually receive these tailored forecasts for, each day from us. But what came to light last spring was that our tailored forecasts actually started to lose their skill. And we realized that this algorithm could actually be used to quantify the impact of COVID-19 restrictions on air quality. And so since the machine learning algorithm already factors in the biases associated with the meteorology and the subgrid scale errors, the difference between the bias-corrected model prediction, shown here for NO2 for Washington, D.C. In red, And then the observations in black is actually the difference between a business as usual scenario and our real life reduced emissions from the pandemic. And so this machine learning algorithm had slightly different updates, including the GeoSCF emissions, because it was relying on the replay segments. And again, he trained the algorithm for each individual site and applied this to over 5,700 sites around the world to quantify the changes in NO2 related to the different COVID-19 lockdowns. And so again, we teamed up with the Goddard SVS team for this animation. And so the circles are colored by the NO2 perturbations. The little green dots indicate if the location is in lockdown. And what you can actually see is how the decrease in NO2 lasted generally long after the lockdowns had ended. And then the time series along the top, it's hard to see, but yellow is Wuhan, blue is Madrid, and then green was New York City. And so this animation carried on through July 31st, 2020. And then Christoph actually extended this through the end of 2020. And so here you can see places like Wuhan, China, and Milan, Italy, had decreases on the order of 50% during the lockdown periods, highlighted here in gray. And in many cities, including Washington, D.C., it just never really returned back to normal. And so I encourage you to check out the paper if you're interested in more details. It was actually released in its final format on ACP website yesterday. And so that's been like it feels like an 8-month process to get it from submitted to final. So very excited about that. Changing gears a little bit here, another application, but this time with external end users. One application of the forecast would be to provide actually a multi-pollutant health-based air quality index. You may be aware that many countries release their air quality warnings using some type of air quality indice or an AQI. And often these are based on just one pollutant, whichever one has the highest concentration. But often, more than one pollutant is high at the same time, and they may have different health impacts. So ozone generally influences the background levels. NO2, it's short-lived, but can have extreme gradients and is often near the sources. And then PM 2.5 drives the spatial gradients, with dust, sea salt, and biomass burning being the dominant features, as you can see here. And so through Brian Duncan's HACAS team over the past few years, we've been working with Kevin Cromar from NYU. He's an epidemiologist, and he's actually translated pollutant concentrations based on health studies into a multi-pollutant health index for children with asthma. And this index actually uses the GeoS-CF maximum daily 8-hour average ozone, and then the 24-hour average NO2 and PM 2.5. Wow, I can't believe I'm already so close to time. Other things that we do. GMAO has a long history of supporting NASA field campaigns. And even since our experimental product in 2017, we've been providing forecasts to some of the campaigns. One of them here is looking at the Owlets campaign in summer 2017. You can see on the left-hand side here is the flight path around the Chesapeake Bay. And the curtain plot has the GeoS-CF ozone in the back and the aircraft model at the front, overlaid on top. And then on the right-hand side is the GeoS-CF ozone compared to 6 surface observations. And so this recent paper by Natasha Datrick really highlights these comparisons and what we actually could both learn about the campaign data as well as the GeoS-CF. Another campaign we supported was the Satellite Coastal and Oceanic Atmospheric Pollution Experiment, or SCOPE. And this was led by Brian Duncan and Ann Thompson at 614 and 610. And BOEM, the Bureau of Ocean and Energy Management, came to them asking if there were any NASA resources that could be used to monitor offshore sources from oil and gas industry in the Gulf of Mexico, which may be impacting air quality onshore. And so this is a tricky place to see from space. As you can see, it's often impacted by clouds in this image of NO2 from TROPOMI. And so they had both measurements on land during the campaign in spring of 2019, as well as they had a cruise out in the Gulf. And we actually supported during the mission planning and post-mission analysis with some specific imagery on the Fluid website. And though COVID-19 has stalled a few of NASA's campaigns, we're quite excited that GEOS products from both FP and CF will hopefully be supporting the upcoming Tracer AQ campaign that's scheduled to be in September of 2021 this year. Very excited. And so the Geocf, like many of NASA's GMAO products, they're designed to be research products and support different NASA activities which measure throughout the full atmosphere. So GeoS-CF, it's not optimized for capturing just surface air quality. We're really looking at the full atmosphere. And so I've already mentioned a couple of field and aircraft campaigns, but we're also have the upcoming TEMPO, the geostationary satellite that's designed to measure pollution over North America, which should be launched next year. And then we also have been working with the Pandora teams and the Tropospheric Ozone LiDAR Network, or TOLNet, which is a collaboration across NASA, NOAA, and Canadian partners to measure ozone in the troposphere and stratosphere. And so I mentioned earlier that we have a way of weakly nudging ozone in the CF system to the FP product. You can kind of see that here on the left-hand side. The black line is the FP ozone, and the pink is the CF. And down to about the tropospheric model layer, we have very good agreement between the two. And on this plot in the middle, it shows the daily range of the increments that are applied to the GeoS-CF, and you can see that there's a hard stop at model layer 35, and no information from GeoS-FP is applied below that. And what we can see then, it's no surprise that the GeoS-CF captures the spread of the OMI ozone column. And so the GEOS-Chem chemistry has a tropospheric stratospheric unified chemistry extension, or UCX, which is largely based on the GMI, the NASA Global Modeling Initiative stratospheric chemistry mechanism, which is considered the gold standard for us when it comes to modeling stratospheric composition. And this was added to GEOS-Chem by Seb Eastham in 2014. Prior to this, it was treated as a simplified upper boundary condition. And so in these figures here, looking at total column ozone on the left-hand side, we have two free-running simulations of GEOS, one with GEOS-Chem, which is highlighted in blue, and the other with the GMI chemistry in orange. And you can see that both are able to capture the observed range and total column ozone. And so learning from these runs, we actually made some updates to the GeoS-Chem UCX and implemented those in July 2019. And you can see that after that, the improvement, which is expected to improve the treatment of with the halogen and nitrogen families.
Sorry, Emma. I think we're getting quite a bit of background noise. Sorry, just whoever is, hello? So whoever is unmuted, please mute yourself. I have a mute on entry, but there's some phones, for example, that I can't mute. So if you're, okay, I think that's a little bit better. Okay. Thank you. Sorry about that, Emma.
No, great, thanks. Yeah, so we can see that after these improvements were made to the stratospheric chemistry at the end of July 2019, we have improvement even in our representation of total column ozone, no longer having that low bias in the southern hemisphere fall and winter periods. So we're currently evaluating the stratosphere, so I won't show too much on that, but I just want to highlight a couple of things, such as during last year's record low column ozone in the winter and spring, when there was a strong northern hemisphere polar vortex. The new real-time GeoCF system was able to provide forecasts, accurate forecasts during that time. So GSFP tends towards climatology, which in March is over 400 Dobson units. And so we can see here in this example from March 5th by Larry Coy that the 5-day GeoS-CF forecast was actually confirmed by the observation-based ozone watch analysis from Code 614 with a decrease of on the order of 7 to 8 Dobson units. And so whenever we have these anomalous situations, the GeoS-CF can really add its forecasting capability. Another example that I like to show, looking again at the polar vortex, we can see that the ozone on the left compared to also some reactive halogen gases. We have hydrogen chloride or HCl in the middle, and then chlorine monoxide on the right at 45 hectopascals in February 2020 compared to MLS observations. Those are the colored circles. And so it's no surprise that the ozone looks extremely good, but it's nice to see that the GeoS-CF is able to simulate the time and location of the vortex as well as the chemistry within the vortex. So it doesn't quite capture the high values of HCl outside the vortex or CLO within the vortex as seen sometimes by MLS. So I do a lot of work on stratospheric intrusion, so I don't have much time here, but I just want to highlight a recently submitted paper to Atmospheric Environment with some work with the TollNet LiDAR group down at NASA Langley. And so we actually were able to investigate in detail this stratospheric intrusion that was observed on Valentine's Day in 2019. And the model was actually able to show that the ozone indeed was from the stratosphere descending over the location of NASA Langley. And this has actually led to a great collaboration with TollNet, specifically working with Matt Johnson from NASA Ames. And during post-processing, I provide him with subset GeoS-CF forecasts at the TollNet locations, and he actually takes that information, produces this imagery, and sends it out to the different TollNet operators. So they receive the 5-day forecast from GeoS-CF, as well as the slightly higher resolution, but only 2-day forecast from NCAR. And with that, they're actually able to make informed decisions as to when to run their LiDARs. So I'm wrapping up here at the end. I've just got a couple of things I want to show. We're working this year now on updating the GeoS-CF, and that would include moving on to the GEOS-Chem version 13, which will hopefully bring some improvements to some of the biases that we remarked on earlier. We'd also love to switch to the meteorology to Gsfp and take advantage of the improvements that have been made over time with things like the 2-meter temperature, which may impact things like the biogenic emissions, where we do see, I didn't show here, but a high bias in formaldehyde over Southeast US. So things like that. Coupling GeosChem aerosols with go-kart aerosols, so we can get the best of both worlds. The aerosol data assimilation that goes in a go-kart, and go-kart could get that information of the chemically reactive aerosols that GeosChem has. And then I definitely didn't have time to show today, but we've been working towards multi-constituent assimilation systems. So the data assimilation system has been expanded to do that. It's known as CoDAS. And so we're working to bring that into the system. And then hopefully today, I've been able to convince you that the GeoS-CF does a great job at capturing the global distribution of the major pollutants. There's a lot more evaluation in the papers that I wasn't able to highlight today, as well as more papers coming down the line. There are things like a recent paper submitted by Matthew Johnson that was accepted in Atmospheric Environment that actually looks at long-range transport of Siberian biomass burning emissions to North America during fire XAQ. So there's a lot coming that will kind of show these evaluation efforts. And then lastly, we actually are working with the Tempo team so that they can use the GeoS-CF replay and forecasts as prior information for their trace gas retrieval. So lots of exciting work and use cases. So I think I'm at time, so I'll just quickly skip over and leave you with this beautiful animation of the complexity of GEOS-Chem. Thank you.
Great. Thank you, Emma, for a really, really great overview. It's really wonderful to see so many applications, and I really liked too how you touched on the validation efforts, and as much as you could go into detail. This is really wonderful. I'll just remind the audience that if you have a question, you can either write that question in the chat. Currently, I'm not seeing any right now, or if you prefer, you can just indicate that you have a question and I can unmute you. So as we kind of wait for that, I guess I just had one question about the Strat-Trop exchange part that I know you've been working on in a couple slides. Perhaps I'm not understanding it right, but are you concerned that that there are kind of any dynamical inconsistencies that might arise in the UTLS region, since you're kind of nudging to the FP ozone aloft, where you show the increments and they can actually be quite large, between that and then just the free running ozone and the troposphere? Is there any kind of suggestion that might produce any inconsistencies in the actual behavior of the folds that you're seeing?
Yeah, that's a really great question. And with the TollNet LiDAR group, we're actually able to dive into that into greater detail. And so it's a bit of a chicken and the egg whether or not they have, in the past year, now that they have these alerts and they're informed as to whether or not to turn their LiDAR on, whether we're capturing more of these examples or not. But then also during COVID-19 restrictions, they weren't necessarily able to all go on site to make these observations, maybe to the extent that they would have done in a normal year. With that, some of the early work, I think, has been consistent with some of the things that we've seen with like the ozone sonde comparisons, where I didn't show this today, but Junhua has done some work showing also the stratospheric profiles for ozone sonde comparisons, and they agree really nicely. And so when we do see biases, they do tend to be in the upper troposphere in ozone comparisons, and that's may be less to do with the nudging, and maybe it's more to do with how lightning is treated in GEOS-Chem.
Okay, great. And the nudging in the stratosphere, is that so you kind of calculate some increment and then you kind of weight it?
Yeah.
Okay. Is it weighted in the vertical or?
Yeah, we nudge it only 20%, so it still allows GEOS-Chem to do most of the work, but even with the nudging, when we didn't have those updates in the model prior to July or August 2019, we could still see that there were biases in the ozone, and so it's really getting the chemistry right that really is I think the biggest part.
Yeah. Great. Yeah, thanks for that. I had one more question too, also about the bias correction. So is that's offline, right? So are there actually two products? So there's a bias corrected one and then unbiased, or is that just?
Yeah, it's the general GeoS-CF that's out there. It's not bias corrected. It's the 25 by 25 kilometer, and so. it's the tailored forecasts are done specific to individual locations, and so that's something that's done after the model finishes during post kind of early adopters of that through Brian Duncan's HateCast work.
Great. Great. So we have I think it's more of a question in the chat about, is it possible that you can share these slides or at least provide a list of references or papers? I think people would like to know.
Yeah, definitely. So on our website, there's information about the GeoS-CF. We have a section on documentation and publication, so we need to start adding these publications that have been recently accepted and published, and so more of those will be added there. You can definitely, if you have specific questions, feel free to reach out to me. Email's also at the bottom.
Yeah,
I'm happy to have the slides shared. I know you said that you're recording it, so
yeah.
There's that.
Yeah, I was just going to add that. Yeah, so this is actually being recorded. And so within about 2 weeks, we should have 1 or 2 weeks, we should have, again, pending, Emma, that everything is okay. We'll have something submitted and posted on the GISS Lunch Seminar YouTube channel. So if you just go to the GISS Seminar site, you can see that for previous presentations, there should be a link to that video. So you'll be able to see that there. So
it's good to know. I might go back and see whose presentations I missed.
Great. Well, great. Thank you, Emma, so much. I can't see any questions right now in the chat, but I think we're all stunned by the amount of information.
Yeah.
So this is really
one thing I'd love to show that I didn't have time. This new capability.
Sure.
Which we actually have like NO2, ozone, and PM 2.5. We've created this GeoTIFFs that you'll then be able to like zoom in on individual locations like I tried to do for GISS here with New York. And you can see the GeoS-CF grid box average. And you'd be able to click on and get the forecast data and imagery as well as historical data and time series. And so it's things like this that we're really excited about that are coming to Fluid.
That's great. That's really wonderful. Nice.
Yeah.
You have. That's great. And so you have NO2, ozone, and PM 2.5. Yeah, that's great.
Yeah. Yeah.
Well, great, Emma. I think we're going to maybe end it right now. We're about 10 minutes after. I want to thank you again. And I want to thank everyone for coming.
Thank you.
And again, Emma said, feel free to email her, or if you have questions about me about this seminar or upcoming ones, please feel free to email me. Again, thank you, everyone. And I hope everyone has a great rest of the week. Bye.
Bye. Thank you.
Yeah, sure thing. Thanks, Emma. Bye.